All right, our next task in describing the ideas of energy, particularly kinetic energy, is to look at the work of a varying force. So, what we've looked at so far is a constant force applied in one direction with the displacement in the same direction. A constant force applied in a direction different than the displacement, and so that led us to this idea of the dot product or the scalar product as the definition of work. Now we need to look at not constant forces. So let me give you an example of a not constant force. Most forces in nature are not actually constant. So a spring is a really good example of a non-constant force. So what happens with a spring? So we've got this spring, we've got it compressed, and here's a mass sitting on the ground, and we're labeling the end of the spring as position x1. And then what we're going to do is, just to make this more simple, we're going to ignore the vector nature of the forces and just consider things in one dimension for this example. So the force is going to push this way and the displacement is going to be in the same direction. So we're applying the force and the mass accelerates away. Now what happens as the spring decompresses is the force that it's pushing with gets weaker and weaker and weaker until finally, once we've reached the length x2, there's actually no longer any force on this from the spring on the mass. The mass is going to go flying off with some new velocity, v2. But the total force looks like this. At x1, we had some large force. Then as the spring decompresses and starts to push this object this direction, the force starts to go down in the spring. It goes down and it goes down and it goes down and it goes down. And eventually it reaches zero, and that's the last force that's acted on this body, and it goes flying off. So the question is, how do we define work in this kind of example? So when we were doing work with a constant force, the graph would have looked like this. If we were to graph F constant, so this would be our position 1, and this would be our position 2. And whatever the force is, it's just some constant number there. Okay? So from position x1 to x2, that would be that the force constant times this delta x, the displacement. We called that the work. We defined that as being the work. And you'll notice that this here, the y-axis here, is the value of the force. So this length here is the value of the force. And this length here is the value delta x. And so it's really the area of this rectangle that is the work done by the force. So it's this area here. We may analogously think that maybe we should define the work done as being the area underneath this triangle. So here, the area underneath the force between x1 and x2, this area, that is the work done in the case of a constant force. Maybe with this varying force, we could define the work as being this. And if we didn't even have a straight line here, we could imagine that we might have something like some force that would behave like this, where we might have, here is our force, and here is our x. And maybe initially it's not very big, and it goes up a little bit, and then it sort of does something like this. And maybe that's x1 and x2. So this is, again, an example of a varying force. It starts off at a value, it goes up, it comes back down a little bit, then it drops off. Another example would be a draw force curve for a compound bow. So the draw force curve for a compound bow looks something like this. At brace height, it's 0, and then it typically jumps up pretty fast, peaks at some peak draw weight, and then drops back down into the valley. So this might be another example of a draw force curve, which is exactly like this. And so what we're going to do is, let's make the definition that the work is just the area under this curve. Okay, so whatever this area is, that's going to be what we consider to be the work done. Now, we're going to make this definition and see if it ends up being equivalent to the original definition that we made. That is, if this work is still somehow associated with kinetic energy. We have to prove that, because now we're changing our definition of work. We're changing it from constant force times a displacement to the area under the force displacement curve. And that's a different definition. So we're going to have to go back and recheck the work energy theory to see if the work energy theorem to see if that still applies. But let's see how we can actually calculate this work in the first place. So let's get rid of this. I'm going to need the space. Let's start with this simple example and ask ourselves, how would we go about approximating? What would be the approximation for this curve? All right, so here's what I want to do. Let's first approximation. We'll do a first approximation first. And what we're going to do is just let's assume that the force is constant. So if we assume the force was constant and we multiplied it by delta x, where this distance here is our delta x, the distance from here to here, I missed that, from here to here is delta x, then notice that we get a somewhat of an approximation. We're really off by a factor of 2, right? Because all of this area is not actually under the curve, but we're still counting it. We're still counting that in our area. But our first approximation is just the force at position x1. We're calling it the force at position x1 times delta x. Okay, and not such a great example, but that's a first approximation. So how could we maybe make the approximation better? So let's see if we can figure out some way to make the approximation better and maybe make this area that we're looking at, that's the error, this whole area above the part that we actually want to count. How do we make that better? Well, here's a way that we might make that better. So what we can do is let's cut the distance, the length, in half. Let's cut delta x in half. Okay, so what we're going to do is we're going to cut this length delta x in half. So now we'll come from here to here. So now this is going to be our new delta x. We're going to call this delta x, and then we're going to call this area here delta x. Okay, and for the first delta x, we're still going to use the spring force here. But then for this one, we're going to multiply this one by the spring force here. In other words, we're going to cut out this area here. So what is our approximation? This is sort of our second approximation. A second approximation is to take f of x1 times delta x plus f of, let's call this point here let's call this point x prime, plus f of x prime times delta x. Notice the delta x here is smaller. So this is the area of this first triangle, or excuse me, this first rectangle, and this is the area of the second rectangle. So notice all of this area that we included in our first approximation, we've gotten rid of. So now our only error are these two little triangles right here. But we can just keep repeating this process. What we can actually do is just do the whole thing again, where we split this stuff in half. And I'm going to have to stop drawing things here because I'm going to start to very quickly run out of space. But you'll get the basic idea. We can take this and we can split it in half, and then we can take the force from here and calculate these two pieces. And then notice what we end up with. We end up getting rid of these squares. Those are no longer going to be issues. Okay. And in fact, what we can do is we can do this. I'm going to erase this down here just to show you. What we can do is we can split these into a bunch of tiny, tiny little segments. And etc. And notice what we get is we get a little staircase here. And those are now our errors. But now notice how the smaller we make these segments, the smaller and smaller this arrow gets. So here we've got some pretty big ones. We've got a big error, but with the smaller and smaller ones, we get less and less error. So let's make a new definition. Let's make the work is going to be the sum over I of f times x sub I. In other words, we're going to take the force at this position here. We're going to take the force at this position here, the force at the next position here. We're going to keep adding them up. And each time we're going to take the force and multiply them by the little width here, delta x, whatever, however wide these little segments are. This little width here, delta x, we're going to multiply them by that. So times delta x. And then we're going to take the limit as delta x gets really small. So as delta x gets really small. In other words, we can keep doing this and cutting these in smaller and smaller and smaller pieces, and eventually we'll get an approximation that's so close to this triangle that we won't be able to tell the difference between the approximation and the real thing. This is sort of like taking a computer screen and giving it higher resolution by increasing the number of pixels. So even though the curve of a person's face on a screen is continuous, it doesn't have little jagged pieces on it. You can go, and if you make your pixels fine enough that your eyes can't tell the difference, you really can't tell the difference between the curve and the pixelated version. And that's exactly what we're doing here. We're making the pixels finer and finer and finer until we can't see the difference between the straight line and a bunch of stair steps that are very, very close to being the straight line. And this will work whether or not we have a straight line force or whether we have a force that looks like this. We can still do the same thing. We can still break this into a bunch of little pieces. And as long as they're small enough, the little triangles that we get, or squares or whatever it is that we happen to get on the edges here, will be small enough that we can't tell the difference. And so this is, in calculus, essentially the process of what we call taking an integral. So an integral is this idea of summing up all these little tiny areas and just doing a whole bunch of them. So we actually write this as the integral of f times the small displacement dx. And we need to say what x's are we integrating between. We're starting at what's called x sub 1, and we're going to what's called x sub 2. So I'm going to change back to my sort of standard writing here and rewrite this. So this is going to be the new definition of work. And that's going to be that our work is going to be defined as being the integral from x1 to x2. So this will be the area underneath this curve of the force vector. Now we're going to combine what we did in the last video, which was take the force as a vector and dotting it with the displacement vector, where the displacement is in what's called an infinitesimal displacement, or a very small displacement. And this is our new definition. So this is the full definition of work with varying forces. The force can do anything it wants to. The force can be some weird thing. It can be a draw force curve, as an example. And we can approximate this draw force curve by building up a whole bunch of little columns in here and taking the area of each of those columns and adding them together. And that will give us the entire area here. And we're going to call that the work done. So this is the work done by a varying force against a specific displacement. And these two things do not have to be pointed in the same direction. The dot product, which is, remember, defined as, I'll just remind you here, that's going to be the magnitude of the force times the magnitude of the displacement, dx, times the cosine of the angle between them, cosine of theta. So we will use this formula. Well, we use this formula to prove the general theorem of the work energy theorem in the next video.